And moreover, just a couple of days ago, Kim Kardashian asked a question about 3IATLAS and directed it to the acting administrator of NASA, Sean Duffy, and he immediately tweeted a reply in which he explained 3IATLAS and so forth. But on the same day, Congresswoman Anna Paulina Luna sent a letter to Sean Duffy asking NASA to release this data that is being held for over a month. No response so far. When I approached the principal investigator of HiRISE, no response. It doesn't make much sense for the politics of the day to sabotage the progress of science. We need this data in order to plan future observations of the object.
After being hidden by the glare of the sun, the interstellar comet 3I-ATLAS has reappeared, and the view is anything but ordinary. Solar observatories, including Stereo, SOHO, and GOES-19, recently recorded a surge in its brightness unlike anything seen in the known catalog of comets. Even more striking, 3I-ATLAS appears bluer than the sun, a chromatic shift that has left astronomers both fascinated and uneasy. What began as a quiet entry into our solar system has become a cosmic spectacle, a celestial event now surrounded by a growing list of baffling anomalies that seem to defy conventional cometary behavior. When 3I-ATLAS first appeared earlier this year, astronomers classified it as an ordinary interstellar comet, icy, fast, and volatile. But as it approached its closest distance to the Sun on October 29, 2025, it began to act like something entirely new. Observations show that its nucleus has sprouted a massive ion tail, stretching millions of kilometers into space, flickering and rippling as if pulsing with an internal rhythm. The timing of its reappearance has created an extraordinary opportunity. By sheer cosmic coincidence, two spacecraft, ESA's Hera and NASA's Europa Clipper, are now crossing through the region of space swept by the comet's extended tail. Neither mission was designed for this. Hera is on its way to the Didymos-Dimorphos asteroid system to study the aftermath of NASA's DART impact, while Europa Clipper is bound for Jupiter to investigate whether Europa's icy oceans could harbor life. Yet, as if orchestrated by fate, their trajectories align to pass through the interstellar exhaust of 3I-ATLAS in late October and early November. For the first time, human instruments may sample material directly from a comet born around another star. The alignment is rare enough to make planetary scientists giddy. Simulations run through a model known as Tailcatcher, software that maps the flow of ionized dust and plasma through the solar wind, suggests that both spacecraft will pass within about 8 million kilometers of the comet's tail. That's far from the core, but close enough to encounter scattered charged particles drifting through the interplanetary medium. Hera, lacking plasma detectors or magnetometers, will play more of a supporting role, helping scientists reconstruct the encounter geometry. Europa Clipper, on the other hand, has a complete sensor suite, designed to study magnetic fields and plasma near Jupiter. It may be able to detect how 3I-ATLAS's tail interacts with the solar wind. If so, the mission could yield the first in-situ measurements of an interstellar comet's physical environment. The possibility has scientists almost gleeful. No one planned for this, yet it may produce data worth decades of analysis. One mission engineer quipped in an internal briefing, "The metaphor stuck. What's unfolding around 3I-ATLAS is a story of scientific improvisation, an unplanned cosmic alignment that could redefine how we study the wanderers that drift in from the stars." But what makes this particular object so extraordinary isn't just its timing. It's the sheer strangeness of its behavior. In the months leading to perihelion, 3I-ATLAS has amassed a dossier of anomalies that would sound implausible if they weren't so well documented. As of early November, scientists have identified 9 distinct oddities, each one statistically improbable on its own, together forming a pattern that challenges established astrophysical expectations. First, its trajectory. 3I-ATLAS travels on a retrograde orbit, meaning it moves opposite the direction of the planets around the Sun. That's unusual enough, but its orbital plane happens to be aligned within just 5 degrees of the ecliptic, the same flattened disk where all the major planets orbit. The odds of that alignment by chance are roughly 0.2%. Second, during July and August 2025, the comet displayed a sunward jet, sometimes called an anti-tail. Most comets exhibit tails that stream away from the sun, sculpted by radiation pressure and solar wind. In this case, however, a bright jet appeared to point toward the sun, not an optical illusion caused by geometry, but a genuine physical outflow moving in the opposite direction. Third, measurements indicate that 3I-ATLAS's nucleus is enormous, about 1 million times more massive than 1I Oumuamua and 1,000 times more massive than 2I Borisov. Yet it's moving faster than both. The combined likelihood of such size and velocity, according to preliminary modeling, is less than 0.1%. Fourth, its timing of arrival appears uncanny. The comet's path brings it within tens of millions of kilometers of Mars, Venus, and Jupiter, while ensuring that it remains unobservable from Earth at perihelion, hidden behind the sun at the precise moment of closest approach. Statistically, the odds of this sequence of alignments are vanishingly small, roughly 0.005%. Fifth, and perhaps most striking, spectroscopic analysis of its gas plume revealed an anomalously high nickel-to-iron ratio, similar to nickel alloys produced in industrial processes.
That along with these objects being nickel-rich, they are also iron-rich. The only other place where we see such an exaggerated proportion of nickel relative to iron is in the industrial production of nickel alloys. It's not as if it's mostly nickel. It's mostly carbon dioxide on the surface. At least that's what we've seen.
Sixth, while most comets are composed primarily of frozen water, 3I-ATLAS's vapor contains only about 4% water by mass, making it exceptionally dry. Seventh, it exhibits extreme negative polarization in its scattered light, essentially the way light waves are oriented after bouncing off dust particles. This effect is unprecedented, stronger than any comet yet studied. Eighth, the comet's incoming direction happens to be within 9 degrees of the source of the legendary 1977 WOW signal, the unexplained narrowband radio burst that sparked decades of speculation about extraterrestrial intelligence. Statistically, that coincidence is about a 0.6% chance. And ninth, as the solar observatories have now confirmed, 3I-ATLAS brightened faster than any known comet, turning bluer than the sun near perihelion. Individually, these anomalies would be the subject of niche conference talks or papers. Collectively, they have become a scientific puzzle verging on an enigma. Astrophysicist Avi Loeb, who has been tracking the object's unusual behavior, calculated that if 3I-ATLAS's non-gravitational acceleration, its apparent push away from the sun not explained by gravity alone, is due to natural outgassing, then it must have lost at least 15% of its total mass in a short time. That would have produced an enormous debris cloud, releasing more than 5 billion tons of gas into space. Such a structure should be plainly visible in upcoming observations through November and December, as the comet approaches its closest distance to Earth on December 19, 2025. If no such debris cloud appears, it would imply something even stranger, that 3I-ATLAS is accelerating without shedding mass, an effect that would have no simple natural explanation. That would become, in Loeb's words, the 10th anomaly. Even as debates swirl around the comet's true nature, mission scientists remain focused on the opportunity at hand. Over the next few weeks, Europa Clipper will adjust its sensors to collect plasma and magnetic field data as it flies through the region brushed by the comet's tail. The readings could show whether the solar wind around the comet is distorted, whether the ions are calm or turbulent, and whether their composition matches any known type of cometary material. Even a null result, no measurable activity, would still carry immense scientific value, helping to refine models of how interstellar objects interact with the solar wind. Until now, astronomers have studied visitors like this only from afar. Oumuamua passed through the solar system too quickly to be studied in detail, while Borisov, though observable, remained distant. No spacecraft has ever encountered material directly from an interstellar object. If Europa Clipper's instruments detect even the faintest whisper of ionized gas from 3I-ATLAS, it would be a galactic first, direct contact with matter that formed around another star. That possibility has electrified the planetary science community. At NASA's Jet Propulsion Laboratory, engineers and physicists have been poring over trajectory data, fine-tuning instrument settings, and running simulations to estimate what the spacecraft might see. Meanwhile, ESA's Hera team has begun preparing navigation updates to capture the precise geometry of its flyby. Even without specialized sensors, Hera's position data can help reconstruct where and when the spacecraft intersected the tail's outer envelope. But as always in space science, there are caveats. The comet's outer tail may be so diffuse that its particle density is vanishingly small, making detection nearly impossible. The solar wind can change direction and speed in hours, shifting the tail like a flag in a storm. There is a real chance that both spacecraft might pass through near-empty space. Still, even that outcome would not be a failure. Null data, one scientist remarked, are still data. Knowing what's not there helps calibrate expectations for the next interstellar visitor. And more visitors are coming. The galaxy doesn't stand still. Astronomers now estimate that several interstellar objects pass through our solar system every year. Most are simply too faint to detect. The discoveries of Oumuamua, Borisov, and now ATLAS have convinced space agencies to design missions that can pivot quickly when the next wanderer appears. The Comet Interceptor, an upcoming European mission, will wait in space ready to chase the next unstudied comet or perhaps another interstellar rogue. What Europa Clipper and Hera learn in the coming weeks could help shape its strategy, from which instruments to carry to how to position for a high-speed flyby. The broader implications are profound. Each interstellar object is a time capsule, carrying the physical and chemical imprint of the system it came from. Studying their composition can reveal whether other planetary systems form comets rich in water or poor, whether their metals are similar to ours, and how radiation and time alter their surfaces during eons of travel through interstellar space. They are, in essence, the seeds and relics of other worlds. For now, 3IATLAS remains both a scientific gift and a riddle. The glow that first startled solar observatories has only intensified. Observers described the comet's tail as turbulent, twisting under solar wind pressure. Some frames show knots of denser material, possibly debris clumps breaking free. If the current trend continues, ATLAS could remain visible to space-based instruments well into early 2026, providing months of data to analyze. The coming observations will determine whether it is behaving like a natural comet pushed by outgassing or something far more exotic. Speculation abounds. Could electromagnetic forces be at play, producing non-gravitational motion without massive gas loss? Could the object be fragmenting internally or composed of unusually conductive materials that interact differently with solar radiation? Or could 3IATLAS represent an entirely new category of interstellar object, one that doesn't fit neatly into the definitions of comet or asteroid at all? These are open questions, and for the first time, they might be answerable with actual data rather than theory. In science, anomalies are invitations. They are the universe's way of saying, look closer. Whether 3IATLAS turns out to be an outlier of nature or a hint of something unprecedented, it has already reshaped our understanding of how interstellar matter behaves under the influence of a star. It has prompted agencies to coordinate across missions, forced engineers to adapt on the fly, and reminded everyone that in exploration, luck is often as valuable as planning. When the data from Europa Clipper begin arriving, expected in late November, researchers will compare the readings against the predictions from the tail catcher model. If the instruments detect magnetic turbulence, fluctuating ion densities, or even subtle shifts in the plasma background, it would confirm that the spacecraft truly passed through an alien comet's influence. If nothing registers, that too will refine our models and anchor future expectations. Either way, this encounter marks a quiet turning point. For the first time, humanity's machines are brushing against the outskirts of a world that didn't originate here, a fragment of another star's story crossing our own. It is a reminder that the solar system is not a closed family, but part of a vast, dynamic galaxy where travelers occasionally drift in, bearing mysteries we never thought to ask. In the months ahead, as 3IATLAS approaches Earth's orbit on its outbound journey, telescopes will watch for that predicted debris cloud. If it's there, it will confirm a dramatic outgassing event. If it isn't, the 10th anomaly, the mystery of acceleration without visible thrust, will deepen the puzzle. Either result will send ripples through the scientific community. For now, the comet glows silently in the darkness, its blue light scattering across the sensors of distant spacecraft, whispering secrets of a world that once circled another sun. Whether 3IATLAS proves to be an extraordinary comet or something we don't yet have a name for, it has already done what the best cosmic mysteries do. It has reminded us that we still live in a universe full of questions, and that sometimes the most revealing discoveries are the ones we never planned to make.